All right, so we've been talking about solubility and how all insoluble compounds have an equilibrium, even though it's very small, an equilibrium constant, which shows that they do dissolve to some extent. Now, there's something called the common ion effect that is relatively important when we talk about substances dissolving, all right? Because these are equilibriums, you can shift equilibriums by having an ion in solution already that is one of the ions that's going to result when our solid dissolves. So, for example, if I have calcium phosphate, and I'm going to see if how much calcium phosphate dissolves, but it's already dissolved in the solution of sodium phosphate, all right? So let's look at our equation. Calcium phosphate is going to dissolve. It's relatively insoluble. It has a KSP of 2 times 10 to the minus 29. But 3 calcium ions are supposed to result, and 2 phosphate ions are supposed to result, okay? However, once these are separate, they come back. And if I start with some phosphate ion already in solution, then more of this is going to be around. It'll be easier for that calcium that dissociated from this calcium phosphate to be snatched up by other phosphate around. So in other words, the ions that resulted when there was a dissociation is in common with the ion that was already in solution. And that's going to drive this reaction towards the reactant's side, because one of the products for this equilibrium is already in solution. All right, and we can identify what the molar solubility is under these common ion situations simply by looking at an ice table. Starting off with 0.1 molar phosphate here instead of 0. If we start off with 0.1, we don't have any calcium, so we still are going to get some shift to the right. So we got plus 3x plus 2x. And now this is 0.1 plus 2x, very small shift, so we can drop that 2x. So 3x times 3x is the equilibrium concentration of calcium. 0.1 is the equilibrium concentration of phosphate. We take 0.1 squared because in the equilibrium expression, the 0.1, which is the concentration of phosphate ion, is squared, raised to that 2, right? 3x cubed, and simplify this, set it equal to KSP, 2 times 10 to the minus 29, solve for x, and that will be the molar concentration of calcium phosphate that'll dissolve even when there's that common ion present. So, here's one for you. You want to try to solve it?
Yeah, I think I can do this.
Push pause, wait for everybody at home, Fred, and then you can keep going.
Are they ready?
Yeah, we're ready.
Okay. So barium sulfate dissolves into barium ion and sulfate ion.
Very good. Is it insoluble?
I imagine so. Let me look at my solubility rules. Yeah, it is. It's insoluble.
Okay, so we're watching it dissolve into barium ion and sulfate ion.
And we got some barium chloride already in solution.
So can I turn this into an ice table?
Yeah, so the initial concentration of sulfate ion, barium ion, looks like it's going to be 1.1 times 10 to the minus 10.
Okay, so KSP for 0.1 molar.
Oh yeah, 0.1 molar. 0.1 molar barium chloride is put into solution.
Very good. So 0.1 molar is the initial concentration of barium, no sulfate. So we are going to have X and X. There's no stoichiometry, just 1, right? So it's X and X there. So this is 0.1 plus X. This is just X. This plus X can be dropped there. So I got 0.1 times X means set equal to 1.1 times 10 to the minus 10. And that's going to be pretty straightforward to solve there, right? 0.1 times X, 1.1 times 10 to the minus 10 1.1 times 10 to the minus 9 then is going to be my molar solubility of barium sulfate in this common ion solution. All right. What will happen to the solubility of barium phosphate if solid barium chloride is added?
This is the common ion effect, right?
Yeah.
Barium chloride produces barium, so the barium phosphate is going to decrease in solubility.
That's right. It decreases its solubility. Now, why is that?
Because the barium ion that's already in solution is going to snatch up any phosphate ions and drive the equilibrium towards the reactants, the Chatelier's principle, right?
Very good. Very good. All right. Now we can talk about quotients and how they relate to the equilibrium. When things are saturated, the quotient will equal equilibrium. But if you do not have saturation, in other words, if Q does not equal K, then you will not have insoluble material in solution. All right? So we have scenarios in which we can partially precipitate out one material, but not a second material, by maintaining the equilibrium concentrations, or not the equilibrium concentrations, but the concentrations of ions such that it's below the actual KSP, so that no precipitate will actually form. Okay, so let's look at this for example. Will the following form a precipitate? If I put in 20 mils of 0.1 molar calcium chloride and 20 mils of sodium oxalate, or sodium carboxylate, will a precipitate form? Well, if I'm told that the KSP for this reaction is, not for this reaction, but for this material is 2.3 times 10 to the minus 9, and the material is going to be what? What is the insoluble material that's going to result when these two mix?
It's not going to be sodium chloride, so I guess it's going to be calcium with C2O4.
That's right. Very good. So CaC2O4, calcium oxalate, all right, it will dissociate to a degree, 2.3 times 10 to the minus 9. But if I put in these concentrations so that I end up with 20 mils of 0.1 molar, 20 mils of 0.1 molar, I can identify what the actual concentrations of my my calcium and my oxalate are, carboxylate, sorry, 2.20 milliliters, 0.1 moles per liter, right? So I have 0.1 moles of calcium ion for every 1 liter, and I've added 0.02 liters. So this tells me how many moles of material I have, and that is 0.002 moles of calcium ion. And then I can identify how many moles of the carboxylate there are. The same way. Start with the molarity, 0.01 moles of carboxylate, C2O4 minus, for every 1 liter. And I have 0.02 liters of that as well. So that is 0.002, no, 0.0002, 2 times 10 to the minus 4 molar, or not molar, but moles of oxalate, C2O4 minus. All right. So I can take my 0.002 moles of calcium and divide it by the total volume, which is 40 mils. Is that right?
I guess. What do you need the 40 mils for?
Well, to convert it to molarity. So I go 0.0012 or 0.002 divided by 0.04, and that's 0.05 molar calcium ion. Same thing over here, 0.01 times 0.02, That's my 2 times 10 to the minus 4 divided by 0.02. That's my concentration. Sorry, no, it's not. Try that again. That's not my volume. My volume is 0.04. I mixed the 20 mils and the 20 mils, right? So I get 0.005. 0.005 molar carboxylate, C2O4 2-. I got the molar concentration of my two components here, and I can multiply them together to find my Q, my current quotient, which, if I multiply those together, I get 2.5 times 10 to the minus 4. Because 2.5 times 10 to the minus 4 is more than 2.3 times 10 to the minus 9, then I know that a precipitate will form. Okay? Okay, very good. Q is greater than K, so a precipitate will form. All right, here's another one. Same thing. You have to find the molar concentration of the lead ion, the molar concentration of the, what is it going to precipitate with over here?
Oh, the chloride ion, lead chloride.
Very good. Be aware that the chloride ion concentration is going to be not 0.001 because there's 2 chlorides for every calcium chloride, right? But in the end, after you find the molar concentration of the lead and the molar concentration of the chloride ion, combine them together in their equilibrium statement, right? Mass action expression. And see if that value is greater than the KSP. KSP being 1.7 times 10 to the minus 5. All right, push pause. See if a precipitate is going to form.
A precipitate forms if it's higher than that value?
That's right. If the value is higher than 1.7 times 10 to the minus 5, the lead ion concentration times the chloride ion concentration squared, right? Then a precipitate will form. All right, did you get it?
I don't think I got it. Can you work me through this one?
All right, did you find, or how do we find the concentration of the lead ion?
That's 0.1 times 0.01, right?
Very good. 0.1 times 0.01. Let's write that out to explain if folks at home don't quite get it. It's 0.1 molar lead ion, right? And which is 0.1 mole, that's 0.1 moles for every 1 liter. And I have 0.01 liters. So 0.1 times 0.01 will tell me how many moles of lead ion I have. All right, so that is 0.001 moles of lead ion.
And then to find the molarity, you have to divide that by 0.02, right?
Okay, because that's the total volume that results, right? So 0.001 divided by 0.02, and 0.05 molar is my resulting concentration. All right, how about the chloride ion?
Chloride ion concentration was 0.002 times 0.01.
Very good, which ends up being 2 times 10 to the minus 5. And then I could divide that by my 0.02 to get the concentration.
Yeah, okay.
So that means that the molar concentration of chloride ion is 0.001 molar. And this is the molar concentration of the lead ion, and this is the molar concentration of the chloride ion. Now the concentration of the chloride ion needs to be squared, right? And I need to see what this Q equals. I don't know whether it's above or below the solubility product. But 0.001 squared times 0.05. So 5 times 10 to the minus 8. All right, that is my K or my Q?
That's Q. K is 1.7 times 10 to the minus 5. So that means that there's no precipitate going to form?
That's right. My current condition is such that I haven't reached the solubility limit. And so even though I added some lead and some chloride into solution, I won't get any precipitate because their concentrations are not enough. Okay, very good job.